So here I'll be talking about some aspects of the breakdown of perturbation theory and its implications for the black hole information problem. So this is some work in progress with Suvrat, which I've been doing recently. And so since this is not exactly in its final form, your questions and comments will be very helpful for this. So now from the title, it may not seem obvious that actually what is obvious connection between the breakdown of perturbation theory and actually what implications, and what implications it might have for the black hole information problem. So for the first couple of slides, let me try to actually motivate the problem which we are looking at. So the first few slides will be actually mostly words. So I hope that I don't actually bore you. So let me start with some introduction. So we all know that perturbation theory is a good approximation for calculating actually most observables of interest if you have a weakly coupled quantum field theory. And and what you find is that at very high loop orders, the perturbation series expansion ultimately becomes asymptotic, beyond which you obviously cannot trust perturbation theory. However, there are certain interesting situations where perturbation theory can actually break down much faster. And so one such class of observables is where perturbation theory can break down, much faster. So actually that involves, for example, large point correlation functions or equivalently scattering amplitudes involving a large number of particles. So so here I will try to quantify what do I mean by large n basically. And so often, so such a large contribution can often happen because of the coherent contribution of a large number of Feynman diagrams to a given process. So let me give you a simple example where actually such a thing happens. So this actually problem was of some phenomenological interest some time back. And so people were trying to actually calculate the scattering cross sections for actually multi-particle production in lambda 5-4 theory. So for example, consider the computation of an n+1 point connected correlation function of the phi z3 level. So say suppose you want to compute an n+1 point connected correlation function at phi z3 level, then what you can show is that what you can show is that at large n, the number of Feynman diagrams contributing to the process actually grows factorially, and because of this factorial growth in Feynman diagrams, the tree level scattering. So in that case, the tree level. So in that case, the tree level amplitude actually has the following scaling behavior. This n factorial is because of the n factorial number of Feynman diagrams which are contributing. So now from this, what one can do is that you can try and calculate for simplicity, let's say the scattering cross section for the production of n particles from some one particle initial state. So it turns out that it is simplest to do these calculations near the kinematic threshold. And what you can do is that you can obtain this following scaling behavior of you can obtain the following scaling behavior for the tree level scattering cross section. And what you can show is that this has this following lambda to the n factorial and some factor which you basically get from actually the phase space integration. So from the phase space, right? Yes. Yes. So you have an right. Yeah. So right. Yes. So right. You have right. So in this case, you have to divide by this 1 by n factorial, and from the scattering cross section, you actually get n factorial squared. So 1 by n factorial cancels. That's true. Okay. Yes. Now, so we see a problem basically because that actually so now from perturbative unitarity bounds, we know that actually cross sections. So from perturbative unitarity bounds, we know that scattering cross sections can't really grow too fast. So to get a sense of why that happens, so for example, in this case, you can write, right. So for example, in this case, you can see that actually, right. So for example, in this case, you can see that, so for example, in this case, you can see that unitarity basically relates the imaginary part of the on-shell two-point function to such the sum of decay rates for various channels. Now, if you right, so now if you assume that perturbation theory is a good approximation for calculating the left-hand side here, so that actually places actually a constraint that so such the cross sections right higher. So now if you assume that perturbation theory is a good approximation for calculating this side, so from there you immediately see that so such the cross sections from this side can't actually grow too fast. So but so actually for the case at hand, we see that from our previous estimates for the scattering amplitude, we see that when you have n, so when you have n roughly scaling as 1 over lambda, in that case you see that the n factorial growth actually completely dominates the small factor of lambda to the n, and also what you can and also you can actually go forward and do like and do say like a one loop estimate of the scattering cross section, and from there what you can show is that the one loop contribution actually scales in this particular manner. So so what this simple example actually tells you is that actually perturbation theory is becoming completely so what this example is telling you that perturbation theory is here actually become completely useless for executing the tree level calculation. So this is one example where you have a breakdown of perturbation theory right at tree level. Okay. So now let me bring in actually gravity into the picture. Okay. So now let me bring in gravity in the picture. So it turns out that for planar scattering means yes. So I will have something to say about this large and yeah. Yes. So yeah. Yes. So as I was saying, when you bring in actually gravity into the picture, it gets a bit subtle because so for example consider defining gravitational scattering amplitudes with respect to path integral of this form, and then what you usually do is that when we say that so if you want to compute some perturbative scattering amplitudes, then you actually do that perturbation theory with respect to some semi-classical saddle point. Now in the situation of breakdown of perturbation theory, actually the gravitational perturbation theory will basically imply a breakdown of locality in this case. So the breakdown of gravitational perturbation theory in this case actually implicitly implies a breakdown of locality, because you usually phrase actually questions of locality with respect to some given metric configuration. So now let's actually briefly discuss what are the implications for this, what are the implications of this breakdown of locality for the black hole information problem. So if you know that, so if you know that actually Hawking's initial formulation of the information problem was based on the question, So basically, what we are saying here is that when you do perturbation theory, you do perturbation theory with you do perturbation theory so with respect to some semi-classical background space type, and and so then the point is that a breakdown of perturbation theory implies a breakdown of so it implies a breakdown of this saddle point approximation, and since and since we will actually phrase questions about locality with respect to some given metric, so so in that case, if the initial saddle point approximation breaks down, then obviously you can't ask questions about locality. So as I was saying, that Hawking's original formulation of the information problem was actually based on the crucial assumption that actually perturbative effective field theory is actually a valid description with respect to these nice slices, what are called these nice slice feature based. So, right. So what are so it's a good description of physics near these nice slices. Right. So right. So actually, but there. So actually, what has been suggested is that a possible loophole in actually Hawking's calculation is the following, that since in Hawking's calculation, so in Hawking's calculation, a crucial assumption was that this assumption that you have a local perturbative description, physics on these nice slices. Yes. So actually, the point here. Yes, but then the point is that Hawking's calculation is right. So, but then the point is that Hawking's calculation is actually reliable for simple observables in effective field theory, and actually you start deviations from actually Hawking's predictions once you have, say, suppose a correlation function which has ordered S black hole number of Hawking quanta, where this is basically the where SBH is basically the Bekenstein Hawking entropy of the black hole. And what has also been suggested is that if you really take into account non-perturbatively small corrections, at the expense of locality, then you can actually restore unitarity to the Hawking evaporation process. And that's, and so it has been worked out in some simple models and so forth. Right. So now we can also put this into perspective in the context of the ADS-CFT correspondence. So in ADS-CFT, we know that so in so in case of ADS, so in ADS-CFT, we know that a crucial criterion for having a low energy bulk, field theory dual description in the bulk, is that so let me actually place this properly. So a crucial actually feature which a holographic CFT must satisfy in order to have some actually smooth semi-classical bulk dual description is that you should satisfy actually the criterion of Largen factorization, which means that if you which means that if you take the correlation function of simple operators, and if the dimensions of those operators actually don't scale with the central charge of the theory, so in that case what turns out so in that case it basically turns out that the leading order so in that case the leading order in Largen, so to leading order in Largen, this correlation functions basically factorize. So this correlation function basically factorize, but actually Largen factorization will actually start to fail if you so Largen factorization will start to fail so Largen factorization will start to fail, say suppose you want to compute a correlation function which has a large number of operator insertions and where the number of insertions actually scales with actually the central charge of the theory, which is, say suppose of order n square. Now by ADS-CFT, the breakdown of this 1 over n perturbation in the CFT would imply a breakdown of actually the bulk G Newton to actually perturbative expansion, and what that means, and so this point I've already said that for such correlators, you can't really have a smooth semi-classical bulk dual description for such observables, and in some sense they cannot be computed within the approximation of so they cannot be computed within the approximation of actually some local effective field theory in the bulk. So in passing, let me also mention what are its implications for the idea behind for the idea of the black hole complementarity principle. So so in a sense, black hole complementarity basically tells us that in some subtle way, the degrees of freedom inside the black hole interior not really independent of actually the degrees of freedom outside the black hole. Outside the black hole, and in some sense the degrees of freedom inside are actually some scrambled. The degrees of freedom inside are basically in some sense some scrambled actually version of the degrees of freedom outside. So actually in ADSCF, so actually with the context of actually some recent actually formulations of the information problem in ADSCFT. So actually what has been realized, so in this case what has been realized is that if you want a bulk effective field theory description, so what has been realized is that if you really want, say suppose like a local bulk effective field theory description, in that case the algebra of bulk observables should be restricted to some small subsector of the CFT, such that the dimension of this algebra of effective field theory observables does not scale with the central charge of the field. And so this gives a realization of and so this gives a concrete realization of the idea of black hole complementarity in the case of ADS-CFT. And and in general, so actually the breakdown of perturbation theory and the breakdown of locality also has and in general the breakdown of perturbation theory and the breakdown of locality in ADS-CFT also has actually important applications for this has important implications for the general program of actually has important implications for the general program of trying to reconstruct local bulk fields in so it has implications for the general program of trying to reconstruct actually CFT duals of local bulk operators. So if we can understand at what points perturbation theory and also consequently locality might break down, so actually that gives us some way of trying to understand how that gives us some way of understanding how an effective notion of locality actually emerges in the bulk. Yes, that's right.
But
that's
there,
right.
you know, like
Yes. Yes.
Yeah.
Yeah. Right. 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 Right.
So that
Right.
breakdown is not say it may be from a classical.
Yes. So from a yes. So from yes, that's right. So from a classical viewpoint, you won't say. So actually, what this is saying is that if you actually believe, so in some so in some sense, what this is saying is that so such a so in some sense, what this is saying is that basically, once you see such a breakdown of perturbation theory, then in that case, what it is signaling, what it is basically signaling is actually that what it is basically signaling is that actually basically you have to take into account non-perturbative corrections into account, and what actually happens is that actually some classical non-perturbative actually configuration actually contributes. So one has to take care of it. Right. So actually this breakdown of perturbation theory here yes. So yes. So now up till now these were merely just words, but so now can we do actually some concrete calculation? So now for yes. So now for actually the rest part of my talk, I will actually discuss a way to actually estimate the scaling behavior of actually scattering amplitudes in the Largen limits of scaling behavior of scattering amplitudes in the Largen limit. So for us, it is actually interesting to actually figure out the Largen behavior of graviton scattering amplitudes. And what turns out is that BCFW recursion relations actually provide a very efficient way of actually for getting such scaling estimates. So, but for the purpose of this talk, I will actually focus on a slightly different problem, and right, I will focus on a slightly different problem, and that involves actually estimating the Largen behavior of bosonic string scattering amplitudes in flat space. Now this, right, and so it turns out that this is an interesting problem in its own right, and whether it has any implications for the black hole information problem at hand. And at this point of time, it's not really very clear whether it has any implications as such for black hole. Right. So here, let me give you a lightning review of how to compute string scattering amplitudes. I'm sure all of you know this, but here I will be writing things in a slightly different way, which actually some of you may not be familiar with. Say suppose if you have read string theory from say Suvrat, right? So say suppose if you have studied string theory from Polchinski, then in that case some of the notation here might seem a little bit different. So here let me just do it anyway. So the basic prescription for calculating string scattering amplitudes is that you take the Polyakov path integral with insertions, which is basically an integral with respect to the space of two-dimensional matrix, which you can put on Riemann surfaces, and and so here the dx mu is basically the integral with respect to the matter fields, which are defined in the world sheet CFT, and yes. So here we know that actually this path integral has So we know that this path integral. So we know that the path integral actually has a lot of redundancies. So we have to gauge fix. There's a lot of gauge freedom in this. Here the gauge degrees of freedom are basically actually diffeomorphisms and Weil transformations. So here we have so here we have to fix actually so here here we would would actually like to actually fix this diffeomorphism and Weil invariance. So you can fix diffeomorphism and Weil invariance by actually choosing a certain slice through the space of matrix. Now usually this actually usually this gauge slice will be parameterized by a certain number of complex modular parameters, which are denoted by m alpha. And it turns out that you have actually 3g minus 3 plus n number of complex modular parameters. And here what I'm doing is that I am actually treating the metric moduli and the position of vertex operators on an equal footing. So in this case, the complex dimension of moduli space is basically 3g minus 3 plus. Right. Now you can consider a general metric variation with respect to diffeomorphisms and Weil transformations, and also with respect to right. So you consider general metric variation of this form, where the first term basically represents actually a change in the metric. Right. So the first term basically represents a change in the metric, which comes from a diffeomorphism. The second part actually comes from a change in the moduli, which is associated with the Riemann surface, and the third part, and the third part is here. And here the third part is basically from Weil transformations. So here the so here let me explain the notation of it. So here the phi so here the phi alpha are basically a set of quadratic holomorphic differentials, which are actually providing a basis for the cotangent space to moduli space for this chosen slice. And as I've already said, that actually delta v and this delta omega, these denote infinitesimal diffeomorphisms and Weil scaling respectively. Now, so now actually using this relation, what you can show is that actually the measured so now what you can show is that actually the measure with respect to the metric actually decomposes in this particular way, where you have the factors which correspond to diffeomorphisms and Weil scalings are basically factored out. and here you have some expression, some Faddeev determinant, and here you have some Faddeev determinant, and you have the measure on moduli space, and you right, so this factor is actually basically the measure on moduli space. So let me explain what are these mu alphas. So these mu alphas are basically actually what are called, right? So these mu alphas are basically called actually, right? So these mu alphas are basically what are known as are right. So in this case, these mu alphas are basically uh, uh, right. So right. So actually, in this case, these mu alphas are actually certain differentials which right. So these are certain right. So these are certain differentials which actually basically characterize the change in the metric when you change the modular parameters. And it turns out that these are basically tangent factors to the chosen slice, which you have. So these mu alphas are basically known as so these mu alphas are a certain differential. Certain differentials, the overlap of which so it turns out that the correct measure on moduli space is basically provided by the overlap. So with this holomorphic quadratic differentials and these Beltrami differentials. Right. So finally, the string scattering amplitude is then basically so after all that song and dance, you can finally express the string scattering. You can finally express the string scattering amplitude in this form, where you have an integral, right? Where finally you are left with an integral with respect to the moduli space of genus G and n punctured Riemann surfaces. Genus G and n punctured Riemann surfaces, and and you have a very particular actually measure on moduli space, and so actually this measure on moduli space is actually known in the mathematics literature. So this get this factor of d mu of WP is basically actually known as the Weil-Petersson measure on the moduli space of genus G and n punctured Riemann surfaces. And so here this factor of delta is yes, so right. So actually this inner products and also so in this case is inner products and so so in this case the inner products and also the Laplacians, which integrate the scalar Laplacian, these are all actually computed with respect to a constant curvature -1 metric on the Riemann surface. So let me actually mention a few more facts about the Weil-Petersson measure. A few more facts about the Weil-Petersson measure. So actually the Weil-Petersson metric admits actually some useful explicit expressions in terms of what is actually known as actually the length twist coordinates on moduli space. And you can actually write down a very explicit expression for the Weil-Petersson tailored form in this coordinates, which takes this form. And actually this parametrization has been actually used by some authors to and this parametrization has been used by some authors to actually calculate so this parametrization has been used by some authors to actually calculate the Polyakov path integral in some cases. And and so actually one more reason why this parametrization is actually useful is that this parametrization also turns out to be useful for the computation of the volumes of these moduli spaces. So actually this will be useful for us. So just a few facts about the asymptotics of Weil-Petersson volumes. So actually recently the volumes of moduli spaces of genus G and punctured Riemann surface actually has been calculated recently, and also now also now in the mathematics literature. Actually the asymptotic behavior of these volumes in large G and in the large N limit are known. So actually these asymptotics will be actually useful for us to so these asymptotics will be useful for us because we want to here to find out the scaling behavior. We want to find out here the scaling behavior of amplitude. Say suppose when the number of we want to find out the scaling behavior of the amplitudes when say suppose the number of punctures or say suppose in the case where the number of punctures is becoming very large. So actually here are some results. Is that what you can show is that the volume of the moduli space of a genus G and puncture Riemann surface as G goes to infinity, and for any fixed n actually takes this particular form. And similarly there, and so similarly you have some asymptotic results. Similarly you have some asymptotic results in the situation where you have the number of punctures going to infinity and for any fixed actually genus greater than equal to. Yes. So with that, yes. So now what we want to do is that we want to actually find out an estimate for say suppose the sphere scattering amplitude. Say suppose the sphere scattering so we want to find an estimate for how in the large N limit the sphere scattering amplitude scales. So for that, yes. So for that we will actually need to bound the various factors which appear in this expression. So for example in this expression you had a product over this function determinants, and we also had this correlation function. So basically in this case what you can do is that it turns out that you can write down the product of this function determinants in terms of what is actually known as the Selbert zeta functions. And so actually the Selbert zeta functions also and the Selbert zeta functions also have some form like this, but this gamma actually basically represents the set of so here this gamma represents basically so here this gamma basically represents the set of simple closed geodesics on the underlying Riemann surface, and here this L gamma is and so in this expression this L gamma is basically the hyperbolic length of so it is the hyperbolic length of this geodesics once you endow the Riemann surface with a constant curvature equal to -1. So now in order to find the estimates, so actually for the large N behavior of string scattering amplitudes, we actually need to kind of bound this function here. So actually for this case you can actually bound so in this case you can actually place so in this case you can actually place a bound on this function determinants. So actually by looking you can place a bound on this function determinants by looking say suppose like at the degeneration limits of Riemann surfaces. So here if we say suppose we so here let's say suppose we introduce say suppose some lower cutoff and say suppose the length of certain let's suppose we introduce some lower cutoffs on the length of geodesics. We introduce some lower cutoffs on the length of geodesics, and say suppose introduce some cutoff, and now so now if say suppose if you look at the degeneration limits of the Riemann surface where some simply closed geodesic pinches off, so in that case what you can show so in that case what you can show is basically that the Selbert zeta functions they are actually bounded as follows. And so in this expression, this lambda n is basically some eigenvalues of the Laplacian scalars. yes. So in this case, this closed geodesic, that's right. So this closed geodesic actually go around cycles, right? And right. Right. Yes. So for a genus G n punctured Riemann surface, you can have actually 3G minus 3 plus n number of these simple closed geodesics. Yeah, the number of closed geodesics is much larger actually. Yeah, number of closed right. So in this case, yeah. Yeah. Yeah, this number is right. Right. Yeah. Yeah. Yes. So actually, with those bounds on, right. That's right. That's right. That's right. That is actually pinching off. That's yeah. Exactly. That is what it is. Okay. So I'm short on time. Almost done. Right. So now basically with this so now right. So now right. So now basically with these bounds on so actually these Hilbert zeta functions, we can actually go ahead and right. So for estimating the string scattering amplitude, we also need to actually place some bounds on the correlation function. We need to place some bounds on the correlation function. Now we can express the correlation functions say in this form, where so in this case the G here is basically so actually the Green's function on the Riemann surface. We can express the correlation function in this way. And so now what you can do is that you can actually write. So now with actually this lower cutoff on the length of simple closed geodesics, what you can do is that you can place some sort of right. So with that lower cutoff on the length of closed geodesics, you can actually place some sort of like so bound on this correlation functions. And yeah, so right, so in that case, what turns out is that you can place a bound on correlation functions like this, and in this case, this factor of n squared basically comes in because in this expression roughly you have n square number of terms. You have roughly n square number of terms, and if you take E to be the average energy per particle, then in that case you can place yeah. So like right, and that is zeros. So here actually this is yeah. Right. So here I'm using implicitly right. So here I'm implicitly assuming that I am actually working with tachyons, but so yeah, it doesn't really matter because actually this form is sort of universal. This form is sort of universal. Yeah, this form is sort of universal. This factor will appear for all correlation functions. Right. Yeah, we could. Yeah, we could get. Yeah. 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 We actually have to be a bit more careful regarding the scaling behavior. Yes, but what we see from here is that basically, as long as E is less than 1 by n, and if you remember that actually, and if you remember, say from this previous expression, that actually the volume of moduli space for a genus 0 and n punctured Riemann surface basically scales as n factorial. Then what you see from this naive estimates that if you try to estimate actually the scaling of the endpoint sphere scattering amplitude, then in that case the infactorial growth of the volume of moduli space actually provides, right, so that actually provides actually the dominating factor here, right, and so that provides the dominating factor. So actually very nicely right, so in that case very nicely the endpoint string scattering amplitude on the sphere will also have this factorial growth. So now what you can do is that so now what you can do is that so now what you can do is that you can also make actually so now what you can try and do is that you can try and estimate the one loop right. So now what you can try and do is that you can try to actually find out some estimates for, say, suppose the one loop amplitude. So in this case also very nicely we see in that case actually the volume of the moduli space. So from this expression you can find this out. So for example we use now this expression, then what you can show is that basically the volume of moduli space for the n punctured torus, the volume of moduli space of the n punctured torus. So the volume of the moduli space of the n punctured torus will actually scale in this fashion. It will scale as n squared times, so actually the volume of the moduli space of a sphere with n punctures. And so actually this actually also nicely tells us that if you compare the scattering amplitude say at one loop, then the scattering amplitude at one loop, then the scattering amplitude at one loop will scattering amplitude at one loop will basically be related to the sphere scattering amplitude in this way. And what this indicates that actually in string perturbation theory itself can break down when you have a very large number of vertex operated insertions, and in fact when actually the vertex when in fact the number of vertex operated insertions starts to scale like this. The number of vertex operated insertions is actually the number of vertex operated insertions becomes actually say so when the number of vertex operated insertions becomes close to 1 over GS, then you see that actually string perturbation theory also starts to break down. So since my time is up, let me summarize. So as we have seen in this talk that actually perturbation theory can indeed break down even at the lowest orders for high point correlation functions, and the breakdown of perturbation theory in case the breakdown of perturbation theory for the case of gravity might have actually important implications for the black hole information problem. And roughly what you can say is that in some sense the notions of locality and a smooth semi-classical spacetime, they actually break down if you start. So so these notions actually start to break down if you probe to spacetime simultaneously with too many points. And then we also looked at the large n scaling behavior of string scattering amplitudes, and we saw that we saw that from so in that case we saw that from our naive estimates, it seems to suggest that actually string perturbation theory can also break down for a large number of vertex operated insertions. But I should also mention that but I should also mention that however these present scaling arguments are actually somewhat crude, and we actually need to make it more rigorous. Hopefully these visuals will be understood.
Computerized saddle point. You think a saddle point might work here?
Yes, so we have actually thought about the saddle point. For example, we are looking so in this case we are looking actually from the computations which actually Ghosh and Mende did. So for example, in this case actually when we were trying to see that if we can actually so we were trying to see that if we can actually replicate those calculations. So in that case basically in that case so if you so if you try to do actually this Grossman calculation, then in that case what you get is so in that case what you get is actually so if you try to do this computation, then you get this scattering equation, what people are calling equations nowadays. And the only problem is solving these equations for so solving this scattering for large n is actually somewhat difficult, but but I think some progress can be made. In this case, if you so in this case, for example, so say suppose you take some simple kinematic configurations. Then for simple kinematic configurations, this scattering equations might be solved. Yes, but that is whether that large n is really so yeah. Sorry. Yeah. Yeah.
I mean, the volumes may not be completely indicative of the scattering amplitude. This thing, I agree that it's it's interesting this thing, but I wanted to just suggest one other context where you know endpoint amplitudes exactly. That is in the non-critical string theories. In the there is this Kontsevich formula for a general endpoint amplitude. It's known explicitly again in terms of a matrix integral. So there, those are in some sense literally scattering amplitudes, though they compute some topological quantities on the moduli space, but they are string scattering amplitudes. And since I think the answers for them are known explicitly, genus 1, genus 0 definitely are known, you could refine maybe the estimate in that case because explicit expressions are available, like this Mirzakhani results that you showed, but they are there earlier from.
So in that case, actually, that can actually provide some better estimates for this calculation. It's actually very nice. Because actually, in this case, actually, what seems to me is that actually the volume actually doesn't capture so actually the full growth, because we have this momentals.
In some sense, it captures a topological part of the scattering amplitude, and probably that might have the leading end dependence. Yeah, because it captures the combinatorics of that.